What this is a test stand. The pump is in the test stand in the jointed tubing. We're using hydraulics and hooked up to this I-beam in order to activate the pump. No different than a pump jack would with sucker rods to activate a downhole pump. And I can play with different pressures to simulate different depths of the well. And what we're going to do is show you how this can pump either both a liquid and a gas, and then go back to a liquid without ever having to miss a beat, which in the conventional system of things that would never happen. So we're going to be activating this pump hydraulically on the test bench. So as that thing starts to pump, it's going to displace fluid. It's going to draw fluid from our reservoir, from our tank. We're going to pull it up a 16-foot hose showing it can actually pull a vacuum, and then it'll charge into the section of the pump, and it'll enter the pump at atmospheric pressure and discharge at various pressures, and we'll be able to see those pressures. Right now I've got this pump simulating a depth of about 5,000 feet. It's innovative, it's thinking outside the box, and what has made the pump work are valves and seals that are innovative to the pumping industry. The gentleman that developed this is truly an inventor in every sense of the word, and so he built the test stand, put the pump inside there, and he's been testing it for over 13 months in his shop. And he'd be pumping air, pumping gas, pumping liquids, and then he needed to find somebody in order to tweak it a little bit, make some improvements. My background was, I was 10 years with a major manufacturer of oil-filled sucker rod pumps, and I took some of the skills that I learned there, applied it to this pump to make some improvements to it, and we've been doing those improvements and testing this pump further in the test stand, and we're to the point now where we want to be able to put it into a gas well and or an oil well and test it and just see what happens downhole. What we've got is our reservoir tank. It's drawing liquids. This is just water with a little bit of inhibited cutting fluid. It's drawing fluid up this hose, 16 feet, bringing it back down into the suction part of the pump. Now you can also see on the downstroke, this fluid level is starting to rise back up the hose. The reason for that is this pump is designed to back flush on the downstroke, so if there's any debris or sand that got on the intake of the pump, it's designed to wash that off on every stroke. We can put that backwash capability on the pump, or we can leave it off. Typically though, we like to keep it on there, so it's back flushing a certain volume on every stroke. And you can see the little black hose here, fluid is being discharged out of there. I'm controlling the pressure, you know, regulating that pressure from 3,000 pounds discharge back, but you can see that there is a volume, you know, being displaced on every stroke. Okay, so that's pretty much empty now of any liquids. So this pump right now is just gathering, it's going to just draw in air. Because this has pumped liquids for a while, it is obviously got to purge itself of some of those liquids, and that's going to take a few strokes before it can get rid of all of that liquid that's been accumulated in the pump barrel.
How high is it going to go now?
It'll probably go to around 2,500 psi. It doesn't reach as much pressure pumping gas as it does liquid because gas is compressible. I'm going to put our intake hose that was grabbing air back into the liquid, and now when I start the pump up, hopefully what should happen is this pump, it will start to pull a suction and actually pull 16 feet of suction on the very first stroke. And as you can see, it pulled a vacuum almost immediately, or it started. So of course it's going to fill that hose, go up over the U-tube, fill the suction, and now the pump is going to start pumping liquid again, going from gas back to an incompressible liquid. One of the unique things too, and you can notice, is that when the pump stopped pumping, we lost very, very little production there on that hose. So now we're building pressure again, pumps displacing fluid, and that pressure should increase to about 2,800 psi. Some people have already come up with a style of pump that's a hydraulically driven unit. It's quite expensive to install the entire system. What we're looking at doing is try and reduce that cost. That's the killer for any oil company, is they're looking at it saying, well, what's my lifting cost? And they need to get that as low as possible in order to make this an economical solution. There's probably 100 and some thousand, 150, 180,000 gas wells that are shut in right now, that are loaded up and are dead and are not producing. So there's a market there. And that's just in, our own backyard. Some of the unique features of this pump are typically because when you see this operating, this pump can actually pull a vacuum, and you'll be able to see that. By doing that, this pump can lower the bottom hole pressure lower than anything that's ever been done that's out there in the world right now. So I can literally lower my reservoir pressure to below zero if necessary, which is unique. Some of the other things that are very unique about the pump are because of the operation of how it operates and the valving that we have in the pump and the types of seals that we have. The compression ratio that we have, this pump has a compression ratio of approximately 3,000 to 1. So with that high a compression ratio, that's why it is truly a compressor downhole. And in a conventional system, the rod string is in tension on the upstroke and compression on the downstroke. The way this pump is built, the rod is in compression, or is in tension on upstroke and downstroke. So the rods never see compression, which is a good thing. Some of the other unique things are that in a conventional oil well, you have to have a certain configuration downhole in order to pump it to prevent the gas from coming into the pump. You don't want gas to come into the pump. We don't care in this pump. So this pump can be ran above the perforations. It can be run below perforations if you want to. It can be run in a horizontal section. It can be run in a deviated section. It doesn't have to land vertically. It'll handle whatever fluid comes into the intake. So that's another first that is very unique to the industry. This is new technology. So where it can be applied, you've heard a lot about coal bed methane wells. Right again in our backyard, lots of places around North America where coal bed methane wells, they make up lots of liquid. If you can get the liquid off the well, the gas will come in. Ideal candidate for wells that have got coal bed methane. There's some fields in Alberta that have liquids. There's not that much water, but it's enough to kill a well. So there's one market there. As long as they give me the parameters of the tubing size, the profile of the nipple, I can probably have the pump built and ready to go tomorrow. If we want to test the pump conventionally with a sucker rod system and a pump jack or hydraulic system, that could be done in a matter of days to test. It's that close. Today, technology is the driver. And I think you're seeing more and more oil companies, taking that role as well. They're looking at that and saying, we better start doing things differently because the industry's changed.